Go ahead.
Got it. Thank you. So my name is Craig Martin. I'm a senior engineer with Owens Corning. I've been with Owens Corning for it's going to be 16 years this April, and all the while I've been with the building science group as part of the company. And the way people ask me what the building science group does, and there's a lot of people in the company that are focused on products and materials, and building science looks at the building as a whole and how the building uh, and materials that make up the wall assembly interact with the environment that it's in, the climate zone, and then also the occupants on the inside. And building science is very dynamic. So when it comes time to like if we're developing a new product, our team will be out there working with installers, working with builders, seeing it put on the house. We also do some data monitoring, install temperature and RH sensors in buildings, and make sure things are performing uh, as we as we suspected or as we had designed them to do. And before Owens Corning, I've done a whole bunch of different things in the construction industry, mostly with energy efficient buildings. Have been involved with Passive House, have been involved with the Energy Star Homes program. I A very long time ago, I worked for a custom home builder as a carpenter, and from there went to work for a weatherization contractor. So doing energy audits, air sealing buildings, re-insulating buildings, adding insulation to buildings. So a lot of the stuff that I learned while I was out in the field doing it. So that's me in a nutshell. Um, Next slide. So uh, briefly, what I'm going to go over is air leakage in buildings, thermal bridging or thermal bridging bridges in buildings, continuous insulation on the outside of buildings, some about durability, and then I've got one slide to talk about savings as we put measures into a building, what we can expect to save, and then I'm going to talk a little bit about products that Owens Corning has in the market. It's a much bigger company than just fiberglass insulation these days, and it's changed a lot in the 16 years that I've been with the company. um, so if we look at a building, um, and I think in thinking about air leakage in a building, all these gaps between building materials, where light fixtures are put in, where outlet boxes are put in, these are all potential leakage paths in a building, and they're all built in to a building. So the when I look at buildings where they leak, essentially it's where the building materials come together. You need to try and figure out where the worst leaks are, seal them, and I'm going to go through some of that here. I have some examples, and then we also, a couple of my colleagues did a study on air leakage in buildings that I'm going to just touch on a little bit. It could be a whole presentation itself, but won't be the focus of this presentation. Um, so one thing to think about when we're looking at buildings is that durability is a big part of controlling air leakage in a building. If you have a 1 inch hole in the outside of your building, and you have some flow through there, some pressures driving airflow through a hole in a piece of drywall, you can move an awful lot of water. So we can get lots of water coming through an air leak. So basically, air transported moisture. Um, we get a lot of people that get concerned about permeability of materials, and if a piece of building material or insulation doesn't have any permeability, it won't have the ability to dry out. But if you have a gap or a hole in that uh, product, there's a lot more air going, or a lot more moisture coming through a hole in a building that is, and I'm going to show you in my next slide, that's permeating through a solid piece of material. So air leaks are important for not only energy efficiency, but also durability, keeping moisture out of the building assembly. So this slide, or a slide like this, has been around for a number of years. We know that a certain amount of air leaks out through the attics, leaks out through the windows and doors, leaks out through the walls, perhaps leaks out or maybe leaks in at the foundation level. And they were all sort of good approximations. And we go back about 12 years ago, a few of my colleagues were trying to answer the question, if we're trying to seal a building, which holes are the most important ones to seal first? And they set about this air leakage study, and they determined that there were 17 leaks in a building that actually leaked the most amount of air. There's some leaks that leak less, some that leak more. I'll go into that a little bit towards the end of this presentation. But in their study, they tested over 1,000 different air leakage sites. They did a combination of sort of lab simulation testing of construction joints, and they also did a excuse me, in the field. We have a few test houses in the back of our research and development facility in Ohio, and they tested um, actual construction joints in the field. 12 months of work, two guys worked on it, and they came up with a list of places that are very important to seal in a building if you're trying to seal and be cost effective about your sealing. And my colleague Dave Wolf was one of the principal scientists that worked on this study. And I remember the first time I heard his presentation, he said, but there are these 17 leaks that leak the most, but none of them are important if you don't seal the big holes first. You know, the way that air, like a fluid, moves through a building, it's going to go through the big holes first, and then it's going to get into the smaller holes as the bigger holes are sealed. So my next group of slides are going to be talking about sealing big holes in buildings. And when I was doing retrofit air sealing out in the field, um, typically what we look for, if we had a house with a real high blower door or leakage number, we would go try to find the big holes first. Um, in sort of modern platform frame construction, it was usually pretty easy depending on the style of the house. Typical houses had typical leakage sites, so we would go find those, seal those, and then if we had additional time, or there was the leakage numbers were still high, we would go to these other areas that I showed in that first slide with all those arrows flowing through it. So seal the big holes first. And a colleague of mine used to say, you need to seal holes that you can sling a cat through from 10 feet. So these are in this building. This is a garage area separation wall between the garage and living space. And this is an area that we have some plumbing running through there. Garage doors, the overhead type garage doors, are notoriously leaky. They don't seal really well. So if we turned a blower door on after this house was finished, we might see air coming out through this recessed can light, and that's essentially because this is wide open into the garage and can potentially be a big leakage path. So something like this, we'd like to see the framer seal. If it's done in a retrofit, you would, or not a retrofit, but if it was done after the framers were gone, we would nail some kind of foam board up here, something air impermeable, and seal it in place. It might be nice to have the framers do it before the MEP goes in, because then they can drill nice holes that are easy to seal rather than trying to fit some air barrier around all these pipes and wires. So this is a area between the floor joists. A similar area is like a knee wall and a cape. Under that knee wall can be a big leakage area. Do we go to our next slide yet? There it goes. So this is we see this in some of the more recent built houses. So this is sort of a double wall here. There's no solid air on the air barrier on the back of here. They might put an insulation bat, in this front sort of stud bay, but behind it, it's sort of wide open out into the attic, and it's an area that can have a lot of leakage. Another place that I would see whenever I saw a house with an overhang, we were immediately concerned that it was open. Like this is a photo that I took on a job site, new construction, but this is the outside and this is back inside looking out, and you can just see daylight coming across here. What they eventually did with this one is they put foam board 1-inch foam board in and sealed around it, so they sealed that leakage area. We see this a lot in raised ranch style houses. I think this was a sort of a colonial design, but anywhere that there's a bump out where there's a first floor over a second floor, excuse me, second floor over a first floor that bumps out, I would be concerned that we'd have a giant air leakage path here. Excuse me a moment. So this is a project that I worked on that was actually in Denver. Um, it was a builder that was building net zero ready homes. They were doing a pretty good job of air sealing. We went in and did some diagnostics because they weren't getting the sort of blower door test numbers that they were expecting. So this is on a second floor. We're looking at a closet here. It was actually the laundry closet. So there's a washer dryer in here, and we had our blower door running. Excuse me, and turned on our we turned on our infrared camera, and what we saw was a lot of leakage along the top plate, and especially right in here. So the whiter or very light color is hotter. It was summertime, so June, so it was pretty warm up there. So when we had the blower door depressurizing the house, it was the air was washing across the inside of the drywall and heating it up, so we could see that leak. So using a blower door and the infrared camera can be helpful when you're trying to find leaks that are not apparent. Um, because this builder was building a number of houses, we went to another house nearby, same design, and we had them put the drywall lid in, and then we had them put a 1 foot strip of drywall down the side. And then we brought everybody that was working on this job site in. We had the plumbers, the insulation contractor, we had everybody there, electrician, site supervisor, and we filled the attic with theatrical fog. And you can see here the fog coming down out of the attic. And what we found is that this was the vent pipe for the clothes dryer, and it was a 4-inch pipe inside a 2x4 wall. And instead of basically they had taken a sawzall to it and cut out a big piece and left it wide open to the attic. The uh, the insulation contractor actually went and grabbed a foam gun and started squirting foam in there to try and stop the leak, but because it was such a big hole, the foam kept falling out, and it wasn't a good way to seal that leak. When you have a hole that's over about 2 inches across, um, can foam will just fall right through it. So having it either the hole cut smaller so the pipe fits through better makes it easier to seal, or perhaps I'd seen people use like a roof boot, like you would use on a vent stack on the outside of a house to seal that joint. This is another project we went into. This is down in Texas. Again, we were looking at where the blower door test numbers were. Again, a little bit higher. You can see that there's a return air here. Um, so we had our blower door going again, of course. Um, Turned on our infrared camera. This was in August in Texas, so it was pretty hot in the attic. And you can see all along this wall, and I'm going to go back to the picture, but it was just um, all the top plates were leaking, and especially around where this chase was. And again, this is a builder that was, probably one of the top 10 builders in Texas. So they were building a lot of houses, and we found this problem across all of their, designs of this type. We did some crawling around in the attic. Not a great picture, but these were the two ducts that were going down into that chase. But it was wide open on top. You could stick your flashlight and look, all the way down to the first floor there. So it was an area of this building that was just open. We took a look at the plans for the building, and we found chases. This, if I go back one, this was where our duct run was open to blow. We were sitting down here taking the picture of that sort of chase there, but this building was full of these chases. and they were not, none of them were capped off. Oh, so uh, in the later construction, we had the framers put a piece of plywood across the top of all of these, and simply by nailing boards over holes and sealing them, we got, tremendous gains in the air tightness of these buildings. um, so that's big holes. Any questions with that, or pretty clear? All right, I'll keep going. uh, Next slide here is back to the air leakage study that my colleague Dave Wolf and his partner Frank Tyler did. And again, what we talked about was, or what the purpose of their study was to figure out, where are the most important places to seal, where are the most cost effective, where are you going to get the most sort of bang for your buck. All right, I think I see a question in chat. Is that right?
Sorry, that was just me letting
Oh,
people
oh,
know that they can ask
all
questions
right,
in the chat.
all right. Yep, saw that. Thank you. Um, so they were looking at the most effective places to seal, where the leaks leaked the most. And again, first we had to um, seal the big holes. I remember Dave saying that. And the other thing that Dave would say when he gave his presentation is don't abandon common sense. If you see daylight coming through somewhere, obviously it's an air leak, and it could be an air leak, and it's uh, even though it might not be a joint that they kind of discovered that was leaking more, um, you know, seal what makes sense. And then while this was sort of targeted at sort of if you were sort of time constrained or budget constrained, these are the most uh, um, important joints to seal. But I remember Dave's response was always, these are the most important ones to seal, but you should still seal everything that you can get to when you're sealing a building. So now I'm going to go through these sort of three areas that they found in their study. So maybe not surprisingly, one of the biggest air leakage areas in the building was at the attic plane. So this is assuming a flat attic with a flat attic with insulation on the attic floor, drywall, and a ventilated roof, just sort of a traditional constructed roof. So anything that penetrated that gypsum ceiling at the top of the building, duct boots, top plates, recessed light fixtures, those are all really critical parts of the building to seal. Um, Doubly with duct work. Essentially, when they install a duct boot in a ceiling and then they use the rotozip tool to cut the drywall out around it, um, there's always a small gap between the duct boot and the drywall. And when you're measuring your duct leakage, you can actually measure some of that leakage from the attic into your system if you're doing a duct leakage test, excuse me, at completion of the building after the drywall is done. Um, and the top plates, if you think about a wood frame building, top plates are going to be at your partition walls. So anywhere you have a wall for your closet or a room in the second floor and your exterior perimeter of your building, there can be, depending on the size of the house, there can be a couple 100 feet of joint there at the top plate. So very important part to seal. The recessed lights were leaking, and these were the lights that they were testing were actually insulation contact rated airtight cans, but they were still leaking a pretty significant amount of money, or excuse me, amount of air, which equals money. Um, the other place that they found that was leaking a lot was the rim band joist. So this is at the framing between floors. Framing can be a little uneven, so it's an area that can leak a lot. Um, in the Northeast here, we have a lot of crawl spaces and full basements underneath houses. So you see this joint again down at the bottom of the building. And then another area that Dave, I remember talking to him about it when he was working on this study, is was the garage house common wall. They were measuring a lot of leakage, at the bottom plate here. We showed earlier a picture with the framing open at the top here. Potentially a direct leakage path between the garage and the house. Hopefully that's already been sealed. But what he was noticing was that there was an air leakage path that was coming under the gypsum in the garage, over the top plate, and then under the gypsum and into the house when he was depressurizing with a blower door. And at first, it didn't make sense to him because it seemed similar to this joint on the outside of the house. There's sheathing and drywall, and they started looking at it a little closer. And what they found is that uh, drywall that's on the garage side of this wall is, for a better lack of better word, it's sort of floppy or um, not as rigid as the OSB plywood or sheathing that's on the outside of the house. They found that it was sort of puckering between the nails, and it was a place where they were getting a lot of air leakage. Um, Not only energy penalty, but in your garage, it can be an indoor air quality issue. You have your car, you have your lawnmower, fuel, you have paint, all of that stuff out there in the garage. That can leak um, fumes into the building and have an effect on indoor air quality. Next slide. So he called these the sort of moderately effective areas to seal, and this is sheathing on the outside of the house. So sheathing to the top plate at the top and bottom of the wall, important part to seal. Plate to subfloor. A lot of times in sort of newer construction, say in the last 20 years, the framers are putting a bead of construction adhesive down here. It's not always done, but it's a pretty important place to seal. Again, same thing at the first floor if you're on a frame deck, not a slab. I've been in houses when I've come up the stairs and you're sort of at eye level with the plate and you can see daylight coming in. These are houses that are under construction. So important place to seal. Maybe a little bit more difficult to seal, in a retrofit application. And when we were working in retrofit, when I was working in retrofit, we mostly focused on the top of the house, the bottom of the house, and any big holes that we could find. And I'm going to go next slide. Come on. So these were least effective joints that he tested, that was tested in the study. And many of these, and I have a list that shows actually how many CFM they measured at the different leakage areas. But all of these areas he was measuring, it was almost couldn't measure the amount of airflow coming through. So between double top plates at corners, vertical sheathing seams that fall on top of studs, bottom plate to slab typically was tight because oftentimes there's sill seal in there. In a retrofit application, or if you're in an older building that is on a slab, it's less likely that they used a sill sealer there. One of the other things that he talked about is these sort of sheathing leaks on the outside of buildings oftentimes are constrained because of house wrap, siding, stuccos. Those type of things can sort of negate a lot of these leaks, or any leaks on the outside sheathing of a building. So this is just a list that came out of the paper that they wrote um, about what they measured of CFM, cubic feet of air per minute, at 50 pascals leaking through the different joints. So an attic top plate uh, leaked anywhere from 0.3 to 0.7 CFM per linear foot, and again, we add up 100 feet of that in a building, it can be a big leak. Duct boots were leaky. Recessed lights had a lot coming through them, and again, these were insulation contact IC airtight cans leaking a lot. and again down through the list here, and then we get to some of these other ones that were on the not as important to seal list, and having trouble. I mean, the blower door doesn't actually register much lower than these numbers here. And that is going to be it for air sealing or air leakage. Are there any questions before I go on to some insulation? All right. So I'm going to talk about a little bit about thermal bridging and its effect on uh, well, performance, and then also comfort in a building, and as well as durability. Um, and this is an example that I've used over the years, but this is a theoretical 1,000 square foot attic. It has R38 insulation in it, and then it has an attic hatch of a half-inch gypsum or half-inch plywood that has no insulation on it. And while no insulation on it, there is still some thermal resistance to the hatch that's there, but not much. And if we do a UA delta T calculation here to get what our sort of effective R value of this assembly is, so essentially a 4 square foot attic hatch and 996 square feet of R38 insulation. If we do our calculation, we have an overall R value, the attic, of just over R29 because this 1 square foot attic hatch is not insulated. So if we take that attic hatch and we put a 2-inch piece of foam board on there, that gives us an R10, and we do our math again, we see that we have increased the R value almost to 38 just by insulating that hatch. Um, the So it just shows the importance of insulating an attic hatch, and then also the effect of having thermal bridges or thermal defects in a building, and how short circuiting a thermal bridge can really help performance. And I'll talk about comfort here in a little bit. So if we look at a building, this is a thermal image or infrared image of a building, one with continuous insulation on the outside, one without. Um, Again, the lighter color is more heat coming through the assembly. The darker color shows less heat. But in this particular building, you can see all the framing. And if I don't know what the cavity R value is here, but if this were a 2x6 house, everywhere that there's a stud in the building, there's an R 5.5. You get 1 R per inch with wood. And then where the cavity is, assuming we have a R20 or R21 bat in there, we're seeing a lot less thermal transfer there. Put foam on the outside of a building, and it can make a big difference in the amount of heat flow, and then also keeping that building warmer, more efficient. And similarly, if we take a look at this 2x6 wall with a R24 blown in, this is a blown in insulation product, and we do our UA delta T calculation again. So we're going to take into account, the framing in the wall. There's more heat transfer where the framing is, or where the studs are, more thermal bridging. A 2x6 wall with R24 in the cavity will have an effective R value of just under 17. Now, if we take that same 2x6 wall and then add an inch of foam on the outside, which gives us an R5, we have a much higher effective R value just by short circuiting the thermal bridge at the framing. And if you look at the sort of nominal R value, it's the same, but the effective R value, because of the reducing the thermal bridge, it's the wall's performing a lot better. So from a comfort and an energy efficiency standpoint, this wall is going to be better. In my work, we do a lot of analysis of building assemblies with a tool called Woofy, and it measures. It's a German software, and it measures moisture, heat, and moisture flow through building materials. So I have sort of simulated here in Climate Zone 5 a 2x6 wall with an R20 bat in it, some siding and airspace, house wrap, sheathing, and then a vapor retarder on the inside and gypsum. And when we're doing modeling with Woofy, we always have a construction moisture kind of built in. So in the beginning, we see a sort of very high peak of moisture, and then in the summertime, as things dry and temperatures are warmer out here, the building dries. As we get back into the winter, you can see it. There's more moisture, so we do see it trending downwards. And the number here on the left side, it's going to be hard to see on your screen, but it's water content. I can't even see it. Water content pounds per square foot or cubic foot, excuse me. So we see that it tops out at 6, and then summertime it gets pretty low. Now we take that same wall, same assembly, and we put that 1 inch of foam board on the outside, siding, air gap, house wrap, vapor retarder, and this is actually a 2x4 wall, so less insulation, so a 3.5, so it's an R15 on the inside. And we do the simulation, and this is over 3 years. We see that it does peak similar to, I'm going to go back to that last slide here real quick. It peaks at a similar height, but it dries and stays dry. And what's happening in this wall is that, I'm going to go back. In this wall, in the wintertime, Climate Zone 5, it's going to be 20 degrees outside, and right here on the inside, it's probably going to be pretty close to 20 degrees. And if we have any moisture from the building that gets through into here, we can see condensation here. We put the foam on the outside of the building. This sheathing stays warm. It stays much closer to the temperature of the inside of the building. So from a durability perspective, and then also comfort perspective, durability, will be less moisture in here, less potential for mold or rot. And then comfort, the building is going to be warmer because of that foam on the outside. And this is a slide that I stole from my old boss, who's now over at the National Lab of the Rockies, formerly NREL. And he talks about when we add all of these things together. So when we control the airflow in a building, when we control the surface temperatures, we can control comfort on the inside of a building. The human body can register a temperature change, I think, of about 1 degree, maybe 1.5 degrees. It can sense a humidity change, I think, of about 3% fairly easily. And what we're depicting, in this photograph is what we call mean radiant temperature. So the body senses all the different surface temperatures in the building, and if they are well built and warm, with not a lot of air leaks, the occupant is going to be more comfortable. And I have a sort of a Three Little Pigs story about this, where I used to live in a house that was built in 1852, so it was very drafty, very leaky. We heated with a wood stove, because that was the only way to keep the place warm. Having something in the corner that was 500 degrees made it comfortable in there. So we had that radiating at us. a friend of mine built a house nearby. He was up on top of a mountain. He built 2x6 walls, had lots of insulation. He had 2 inches of insulation on the outside of his building. He had triple glazed windows. Building was very airtight, and he set his thermometer for his heating system on 62 degrees. And I always felt sort of warm as toast when I was at his house. But I'd go back to my house, and because it was poorly insulated, very drafty, um, and lots of thermal bridging, my thermostat would say 68, and I would feel cold in my house. So it was a sort of, I lived in the I lived in this box, but in not in the good one, the bad box. So that's the last slide that I'm going to talk about, thermal bridging and durability. Any questions there? All right. The next thing I did was, um, we use another tool, software tool called Ecotrope. It's used for modeling energy use in buildings. Um, we use it for sort of simulating performance uh, internally when we're looking at products uh, going into wherever different climate zones. If it's a new product, what potentially we can use it for savings. Many builders across the country use it for code compliance reports. It develops or it generates a HERS score or the energy rating index score, and allows the builder to apply for their building permit and get the necessary paperwork to the building official. Um, so what we've done, or what I've done, is we have a sort of standard house. It's a NIST building that we've adapted for just using as a study. It has a we'll change whatever parameter that we want in it. But with this um, sort of example here on this slide, we had our standard 2-story house. I didn't change anything else other than the things that I listed here. So I started with, I thought might be a pretty bad house that you might run into, or a pretty bad building. And this was it's about a 2,200 2,250 square foot building, 2 stories, 3 bedrooms. And what I did is we ran a base case. So we had uh, the air leakage set at 10 air changes at 50. We had the attic insulation at R19, and that the walls were insulated with nothing. So the wall cavities were empty. And everything else, every time we kind of step down this curve here, nothing else changed other than what was listed here. So we didn't change the lighting or the efficiency of the heating cooling system. We didn't change windows or doors. We just changed, just kind of pulled one lever. So this first house, we on the sort of base case, we went to this next step, which is, what I would do first is try to air seal the building, try to make it tighter. So we optimistically said, we could get from 10 air changes to 5 air changes. Everything else stayed the same. And we dropped started at 1900 therms of gas to heat, and there's 100,000 BTUs in a therm. So this is 190 million BTUs, and this is over a year. So it's what we might see for savings over a year. So it dropped down to 1,386 just by air sealing. The next thing that we did is, I like to go to the biggest, easiest things to do first, or where we're going to get the most effect. So we had no insulation in our walls. The next step was to blow in some insulation. So we had 2x4 walls. We blew in a R13, and you can see that made another really big drop to go from zero insulation in the walls to an R13 wall. So very cost effective to do something like this. Um, The next thing we did was in the simulation was we went from our R19 attic to an R49 attic, and we see you don't see as big of a drop here, but we did gain some efficiency here. Um, a lot of the retrofit programs out there always insulate attics. It's a very easy place to insulate. What there might be a question of why we're not getting as much savings. We're going from 19 to 49. You're always going to get more savings when out of your sort of first inch of insulation that you put in. So if something has 0 and you put in a lot, or you add it, go to 13, you're going to get a lot more savings than say going from already having an R19 to a R49. The last thing we did was we added uh, an inch of insulation, so continuous insulation on the outside of this building. So it went from that uh, R13 wall, put 1 inch of foam on it, and we got a pretty decent amount of savings there. And a house like this, 5 air changes is getting pretty close to a code built house at this point. Um, but is there room for improvement? I didn't get into this part, but we could do something like a new heating system or new windows, something along those lines. What Oh, I see a typo in here. I'll cover it. Um, what what I think that when you're looking at retrofitting a building, again, low hanging fruit are, I think, air sealing and anything that's not insulated, then attic. We're probably not going to put an additional layer of insulation on the outside of a building unless there's a reason that the siding has to come off. That's an opportunity. Um, so we typically the cost effectiveness of adding an inch of insulation is going to go not be cost effective if you're ripping off the siding and putting new siding on. Any questions here? No. All right. So now I'm going to talk about some of the products and resources that Owens Corning has. Um, Owens Corning has been manufacturing fiberglass insulation for, I don't know, something like 80 years now. Um, it's a it's a product. I mean, a lot of people think it's an old-fashioned insulation, that it's the same stuff that maybe my grandfather put in his house. And while it's related, um, the the teams that work in our R&D facility and then also in our plants are always looking at ways to improve the product, make it have better recovery when you open up a package. It gets compressed when it's put into the package after manufacturing. And this insulation here, that Next Gen, is our latest formaldehyde-free new binder product that we see in buildings. So it comes in all different shapes, sizes, lengths, bats, and also rolls. The If I put in a picture that had all of the products, you wouldn't be able to read anything. So I went with this one. Another product that we use a lot in retrofit is our unbonded loose fill. So this blows in with a truck mounted blower or a blowing machine. We can blow it into attics in new construction, in retrofit. We can net and blow walls in new construction. So this is a, a basically a fabric. It's almost like a landscape fabric. We staple it up, uh, poke the hose into the wall, fill up the cavity. It's a really great way to insulate a new building. It fits irregular cavities really well. In retrofit, we have some contractors that are using it in retrofit, not lots, but there are people that are doing drill and fill with our loose fill insulation. And the other product that Owens Corning has been manufacturing for 30 or so years is Fomular, which is an extruded polystyrene insulation. Um, this is probably the most popular one that you'll see on a job site. It's the F250 product, so its compressive strength is 25 psi, so it's pretty high compressive strength. We have product that goes all the way up to 100 psi that's used actually in road construction, goes under road beds and rail beds way up north, like Alaska, Canada. Um, we don't see a lot of that on job sites, but it is something out there, and we're using Fomular in on foundations, inside foundations, on walls, um, many applications. A lot of it gets used to insulate concrete, what we see here in the Northeast. A new product that we have been working on in the development of, and I've been involved in the field trials, is a structural sheathing product. So it is the same Fomular board that we've been manufacturing for many years, but it has a polymer sheet on either side, and essentially the board turns into your sheathing. So you don't need to put plywood or OSB sheathing on a building. This product has a shear strength. Um, it is your insulation. It's your water and air barrier. You tape all the joints, and it doesn't need to have house wrap put on. So it's a brand new product in development for the past 4 years, and we just launched it a few weeks ago at the International Builders Show. Um, this might not be something that you would use in a retrofit application, because it typically a building is already going to have structural sheathing on it, and going through this product certainly costs more than the sort of the standard Fomular. So retrofit, probably not going to be something you use. We are looking at um, a product that has the structure, or the polymer on one side. Because the one nice thing about the polymer that's on here is it can act as a nail base. So you can staple to it, you can nail to it. It has high nail retention strength, and it'll pass the pull test. So we're looking at making a version of this that doesn't have the polymer sheet on the backside, so it would be more helpful in retrofit. But that's going to be sort of down the road, um, in version 2 or 3.0, as we go into development and see how this stuff works in the market. And now I'm going to talk about a couple of things that typically when people think of Owens Corning, they think of fiberglass, or maybe they think of shingles or a Fomular. And since I've been with the company, there's been a lot of growth in the business, and merger acquisition. And probably about 10 years ago, Owens Corning, Thermofiber became part of Owens Corning. So Thermofiber is a mineral wool insulation um, used in sound assemblies. It's also used for fire safing. I'm going to mention a little bit more what we do with Thermofiber, but you can buy it in standard bat sizes for insulating buildings, residential and commercial buildings. Owens Corning, probably about 3 years ago, bought a company called Natural Polymers. So they're a spray foam company. We can we sell an open cell and a closed cell spray foam. The chemist, or the person that founded the company, is using on the B side of the spray foam, is using some more natural oils, and that's why they're calling it natural polymers. But it is a more I'm not going to say environmentally friendly, but the way that they've designed it is that the reentry times are lower. So you can see the guy is, in a or sort of, I wouldn't say spacesuit, but he has remote air breathing. You don't want to get in contact with this stuff when it's being installed, but it has some great properties around air sealing. And in retrofit, I've seen people use this in sort of tough to get to areas. Rim band areas are a great place to put spray foam and retrofit. Um, I've seen some people actually pull all the insulation out of an attic and then do what they call a down spray. They'll spray just a thin layer of the spray foam on the attic plane, and that will air seal, and then they'll fill the rest up with some kind of loose fill insulation to make up the rest of the R value, and and in that way, cost effectively using the air sealing properties of spray foam, but then using something that costs less to get the R value that they need for performance. I mentioned roofing. So there's a large part of the company that manufactures roofing underlayments and all the components involved in putting asphalt shingles on a building. Um, what I am told is that uh, Owens Corning developed a roofing shingle that was based on using a fiberglass mat product. And at the time, all shingles, asphalt shingles that were out there were based on a wood fiber base, sort of like a tar paper type base. And then the granules were put on it, and that's how the shingles were made. Owens Corning developed a process to um, instead of use the wood fiber paper, they basically made a glass mat paper and developed a more durable shingle. They couldn't get any of the roofing companies to buy into it, so they started their own. Owens Corning started their own roofing company uh, with the glass mat fiber as the base for the shingles, and now all of the shingle manufacturers manufacture with a glass mat sort of base for the shingles. So it's a standard now. Um, and over the last few years, Owens Corning has merged with a company called Masonite. So we have a door side of our business, and then we also have a composite lumber business, and our composite decking business, what we call marine grade decking. And getting near the end. There's also a large part of the company now that is involved in commercial and industrial applications across North America, Central America, South America, and Europe. We manufacture many different pipe insulations made out of cellular glass or foam glass, shown here. We have a pipe insulation and ductboard made out of mineral wool. We have fiberglass pipe insulation. We have fiberglass ductboard. We have a product, FDM, that we sell to the flex duct manufacturers that our insulation goes into. And probably one of the biggest markets for the mineral wool that Owens Corning manufactures is into um, curtain wall construction and fire containment. So all of the components on here, the fire shield, the fire safing with mineral wool, and the clip system is something that Owens Corning um, manufactures. Um, and one thing, I did not get a slide in here about, but when I'm looking at the duct work, we've been doing some work with burying burying ductwork in attics under loose fill insulation. We've done some work in retrofit where new duct systems were we putting into existing houses. All the insulation was vacuumed out of the building. We put new ductwork in. We put it down at the bottom of the attic, right, basically on top of the ceiling, and then buried it in insulation. And we're finding that it's as the building codes get more strict, energy codes get more strict, we're finding it's a great way to make a duct system much more energy efficient, almost as energy efficient as bringing it inside of a building. So retrofit burying ducts can be a good strategy. And there, I was asked to talk a little bit about the product availability, and I talked with our area sales manager here in the Denver area. He covers Colorado and actually all the mountain states. But we have suppliers, IDI and RAS Insulation both have warehouses on the north side of Denver. They typically sell to insulation contractors, but people can go in and buy insulation from them as well. We have a couple of bigger insulation customers here in Denver. Spec 7, they mostly work on new construction insulation. And then Net Zero Insulation is a contractor that does work, I think, in all of Colorado, doing retrofit air sealing and insulating. And as I mentioned, our salesperson here, our area sales manager, and covers Denver is Emmett. So all resources that would be available if you needed them. And that was my last slide.
Okay. Can you hear us?
Yeah, I can hear you now.
Okay, great. Yeah, thanks for a very informative talk about all the product as well as the applications. We have a few questions here, at least in the room, but Nick,
Yep.
maybe you can go through the chat if there's any. But
There's one question in chat. So I'll go ahead and ask that, then we can go to your room, and those online, if you have other questions for Craig, feel free to add them to chat or unmute and ask. So this came in from Todd Allen. How effective are like thermal cameras, wizard sticks, to help identify energy saving opportunities? Could this be something that, nonprofits did on their own, or, how should someone go about doing these kinds of assessments?
So the price of infrared cameras has come down tremendously. Like when I first got into the industry 35 years ago, the only people that owned them were the utility companies because they cost, I don't know, $50,000. 25 years ago, a handheld thermal imaging camera cost about, I don't know, $20,000. And I'm going to take a step over here and grab something. Lear makes these little handheld. It's disappearing into the. So they make these small handheld infrared cameras. There's some attachments that you can buy for cell phones, but I think that they can also be somewhat misleading. So I think that probably some training would be helpful. A number of the vendors that are out there that sell thermal imaging also offer classes. One thing that a lot of the cameras do is they auto range, so they will kind of take the high and low temperature that's in their view and will adjust the range so you see the differences. And you can look at one wall and be like, oh, I can see the framing or whatever, and then look over at another wall and the temperatures might be different, but if you're not careful in the auto range changes, it can give you like false positives, I guess. So the I guess if the advice would be to make sure you have some training and understand what you're looking at, so you can kind of make educated assessment with a camera, infrared camera. And, I certainly like using them for kind of diagnosing problems. They're also really good for teaching, right? You can kind of show people where air leaks are happening because it's visual. There was a point in time when I was doing retrofit air sealing where we would spend a lot of time, using smoke pencils, doing pressure differential testing, infrared cameras, and really what it came down to is that we knew where the houses leaked, and we just went and found them and sealed them. So it was good for learning, but and maybe teaching, but not not the tool that you absolutely need.
Great. And I'm going to stop the recording now.
Okay.
So